Welcome to everyone out there joining us today on Facebook for our monthly Rockin pop-up with Gavin and Graham, the Geology Gents. My name is Marisa Gomez. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History. And if you have tuned in to these in the past, you know, well, I'm just gonna do this as like a little surprise without introducing it, because I've got a surprise for Gavin and Graham too. Okay, this is something that I don't know if this is gonna like stand out as something relevant to you guys or not, but I'm very excited about it because did you notice something different?
There we go.
Oh my goodness.
So every month, Gavin and Graham pick out these special pictures that they have behind them that tie into what they're going to be talking about. And I've never been able to join the fun because I was technologically deprived, but no longer. So I got some rocks behind me. These are from the museum's collections. Actually, I think Gavin and Graham, you helped us like figure out what these rocks were, right?
They look familiar. Yeah. Those are some nice rocks.
This was like a donation a couple of years ago. But anyways, I'm just very excited about it. So maybe next time I'll match you guys. But let me know what are we looking at behind the both of you today?
Well, Marisa, these are the famous White Cliffs of Dover.
I can see that.
So, Graham, tell us a quick bit about the White Cliffs of Dover and why they are relevant to what we're talking about today.
Yeah, so these are all the way across the pond in England, in Dover, in fact. And these white cliffs are all made up of a type of rock that we're going to be talking about today. They are made up of biogenic sediments, and that's a big word, but we're today going to be talking about rocks that are made of things that used to be alive. So usually we think about just fossils, but there are whole rock units, huge units that cover, hundreds and thousands of square miles and are, hundreds to thousands of feet thick that are all made up of little critters.
That's right.
Can't wait. Yeah, and you just said something about like a long word, and I know that we've got a lot of those coming our way. So everyone, buckle up.
Yeah.
But yeah, take it away, guys.
Awesome. Here, all right. So like I said, today it's all going to be about things that were alive. So Gavin, can you give us just a quick little preview here on this slide of what we're going to be talking about today?
Okay, Graham. So you've got some close-up images here. Across the top, we have these little weird-looking critters. Those are all single-cell organisms. So when we're talking about it was alive, we're talking about millions and billions of these single-cell organisms. Plankton, often folks know plankton in the oceans, but when you have big blooms of these plankton, and so all of these little organisms are making a little shell, and when they die, the shell falls to the ocean, and those make big sections of mud. And depending on what is in that shell, what the organism is making its shell out of, those muds are going to be of different types of rock. And that rock can form, giant cliffs like the ones we see behind us.
Yeah, that's absolutely right. So let's dive right in and get into sedimentary rocks. So Gavin, we have a couple of Rockin pop-ups that we released a while ago about sedimentary rocks and how they form in basins. So when we talk about a basin, what do we mean in a geologic sense? What's a geologic basin?
Well, Graham, it's just a place, a depression in the topography of the earth, the sort of like ups and downs of the earth. So when you have a depression, you can have sediments accumulating. So think back to our Rockin pop-up about sedimentary rocks if you want to know more. But if you want critters to accumulate, like we were describing, you go to a basin. So most of the basins we'll talk about today are the ocean, because that's where you get enough of these critters and enough of these sort of dead critters on the bottom of the ocean to form rocks.
Yeah. And I think another key thing that we're going to be mentioning today is not only are these basins important as places of collections for these material, but basins also tend to hold water. And we know that water is the molecule of life. And so if we're going to have lots of things growing and making shells and bodies that can turn into rock, we're going to need a lot of water. And there's nothing better than the oceans or lakes, and any place where you have large bodies of water that are full of good old nutrients. So but also our clastic or our rocky sedimentary rocks can also form in basins. And that's where we can lump together things that are just made out of rock, right? There's no living organism parts that go into those. And like Gavin said, we've spent a couple of Rockin pop-ups in the past talking about those. So here's a classic one, the conglomerate, big, chunky, round river rocks that are clumped together in mud. Well, you can make rocks just like that out of shells. And here is probably the sort of coarsest grain, the kind of chunkiest, crunchiest biogenic sedimentary rock out there. This is coquina, and this is basically just welded together shells.
That's right, Graham. I remember when I was learning sedimentary geology in my SedStrat class as an undergrad, and I would always love to identify coquina because it's like, oh, that is just a rock that has a bunch of big shells in it. But even sort of the carbonates that we're going to be talking about today, like the ones behind us, you can't often see the shells as obviously as in coquina, but it's pretty much the same exact process. You just have these tiny, tiny little shells forming these rocks.
That's right. And so in order to make these big rocks, right, they're covering big areas. So we need a lot of critters. And so this is where algal bloom come into play. So we're going from big chunky shells, oysters, clams, snails, and we're going to zoom all the way down to things that are thinner than a strand of human hair. So most of these little microscope images over here are at some of them even have little bars tucked onto them, but these things are only about 10 to 20 microns across, and a human hair is about 30 microns. So we're talking about really, really small things, but they're making these armored shells to cover and protect their bodies as they're hanging out in the water column. And Gavin, what are these things chowing down on?
Well, Graham, they're chowing down on nutrients, right? Like pretty much you have a lot of these blooms happen when you get a flush of nutrients into the ocean. And the type of nutrient oftentimes is going to dictate the type of shells you get. So if you get like a bunch of the element silica into the ocean, you'll get silica-rich shells. If you get a bunch of calcium and iron and other stuff, magnesium, oftentimes you'll get calcareous shells.
That's right. Yeah. And so we're going to go in and we're going to break down these different types of shells a little bit more. But the other cool thing about these is these are like the plants of the ocean. These are algae. These are plankton. These are the tiniest little critters that live up in the water column and are eating sunlight. They're eating nutrients and using sunlight, and to those things together, they're using to grow and make these shells that armor themselves. And so, yeah, depending on what nutrients are available, some of them will be really happy and build their bodies, and others will, stay to the side, and then, they'll sort of switch off depending on what nutrients are available. But these are big things covering hundreds of miles on the ocean sometimes. And there's just tons and tons of these little critters. And this is actually what some of them look like when they're alive. They reach out these long feelers to sort of grab all those good nutrients out of the water column. But enough talk about algal blooms. Let's start thinking about, why these things end up making so much rock is because there's just so much ocean, and there's so much good place for these things to grow and live in the ocean, that actually most of the earth is covered in biogenic sediments.
This is just an amazing map, Graham. When you showed me this, I was just kind of mind blown that like most of the ocean sediments that we think about that are, in the middle of the ocean, that aren't adjacent to the continents, are going to be these like different, made up mostly of these different shells. So the basically the light blue here and the yellow here are the ones that we were specifically talking about, but these are sort of like pretty much just shells of these algae.
That's right. So they're blanketing a ton of the earth. They used to blanket all sorts of other parts of the earth, but these biogenic rocks are a huge component of the sedimentary rock archive on Earth. So let's bite into some of these rocks. Let's start out with one of my favorite, good old limestone.
Graham, I mean, this is a good one to start off with because limestone's all over the place and close to home in some cases. So limestone is made up of the mineral calcite, right? So what kinds of algae would we expect to make limestone?
Yeah, so we would expect the sort of algae that makes limestones to be ones that are having a blast when calcium is around, ones that can gobble up so calcite is made out of calcium and the carbonate ion, and that's as much chemistry as I'm going to share on this point. But they take those two ions and they put them together and build shells out of them. It's actually the same thing that chalk is made out of. And a little spoiler for something we'll talk about in just a minute, it's what a lot of the bedrock around Santa Cruz is made out of in the form of marble. But before we get there, Gavin, these things build their shells out of calcium carbonate. So they're all hanging out in the water column, eating and having a good time like this guy. And then what happens?
Well, Graham, the circle of life happens. They die and they sink to the bottom of the ocean. And their skeletons just kind of build up. And it makes this sort of mud. Geologists like to call it an ooze.
Yeah, that's right. And this calcareous ooze, as it gets buried beneath more thing, solidifies into a hard rock. Those shells kind of fuse together and they cement in the spaces between them. And that makes limestone. And we don't have a ton of limestone around here in Santa Cruz. A place with a lot of limestone is actually where I grew up in Wisconsin, where there used to be a deep interior sea or a shallow interior seaway, and it was warm and all these critters were having a great time gobbling up nutrients and sunlight. And so there are these huge areas of limestone that are, around 400 to 500 million years old, that just sort of blanket the Midwest from where there were these ancient seas. But then, Gavin, something really cool about limestone is that if you squeeze it and get it real hot, what happens?
Well, Graham, I think the listeners at home will recognize what we're talking about. It turns into marble, and we always talk about that because it is close to home. So we have a lot of marble around here. So there used to be a ton of limestone in Santa Cruz, but because Santa Cruz is such a tectonically active place, you're getting a lot of squishing of the rocks, a lot of exposure to heat and a lot of exposure to pressure. All of that limestone has since turned to marble.
That's right. And since, so Gavin and I are up here on the UC Santa Cruz campus, and beneath our feet, it's all marble. And that had started out long ago as limestone. And before that was just a bunch of critters in the water column.
That's right.
All right. But let's take a quick step aside from limestone and talk about another awesome calcareous rock. Gavin, this is the image behind us. This is one of the most striking sedimentary rocks on Earth. Tell us about the White Cliffs of Dover, please.
Well, Graham, it's actually very close to limestone, but the thing that makes chalk special is that it's very, very, very pure. So what happened was that you didn't have a bunch of like clay minerals and other rocks that were contaminating these muds that these critters were making. You just had a ton of these critters called coccoliths, which you have a picture of down here on the right, and they just continued to blanket the base of the base of the ocean, and there were so many of them that they got really, really thick. This mud that they made got really, really thick, and it was just white because there was nothing contaminating it. So chalk is also the mineral calcite or calcium carbonate, but in this case, it's just so pure. It makes this white, beautiful chalk or limestone.
That's right. And Yeah, and they've got these coccoliths have these really cool, just sort of platy armor around them that I'm always really struck by. That it's a lot of these things have a single sort of solid skeleton, but these guys are just like it's like a bunch of umbrellas that have been like pulled together, and they look pretty cozy in there. But you know what? It's not all calcium and carbonate at the end of the day, is it?
It's not, Graham. And one of my favorites is chert. So I'm really happy we're talking about this silicious oozes. So we talked about coccoliths and some of the other radiolarians is another one that they're these critters that like calcium in the water, but not all critters like calcium. Other critters like diatoms, shown here, like silica. So if you have a bunch of silica in the water column, you're going to get the same sorts of muds, but the muds are going to be made out of different stuff. In this case, we call them silicious oozes because they're made out of most of the silica. And you get, Graham, not minerals, but what types of samples from what types of rocks from
Yeah. So once those silicious oozes make it to the seafloor and get buried beneath a bunch of other stuff, they get warmed and squeezed, and those silica shells start to fuse together. These diatom and radiolarian shells start to fuse together, and those form the wonderful rock chert, which is almost identical to glass. What happens is all these little tiny crystals fuse together, and they're not really left with a strong crystal structure. And so you make this amorphous or non-crystalline, right? So it looks just like glass rock called chert. And so you go from these crunched up little diatom and radiolarian tests is another word for their shells. And then once you pack them together, they just sort of fuse together and turn into these just sort of blobby, dense rock that looks like this, beautiful, dully reflective chert, which is just a beautiful thing.
It's really cool, Graham. And for all of you archaeology nerds out there, chert is oftentimes what arrowheads are made out of because, as Graham said, it doesn't break like a rock where you break it along the crystal edges. It kind of breaks in these shards, so it's easy to sharpen, and that's why they make it.
Yeah, and chert is also, or flint is also a type of chert. So that's another familiar rock that has been really important in human history. Cool. So we talked about cherts, we talked about limestones, we've got the two main rock types. But Gavin, there's something also that's cool about carbonates is that they've been a really important bellwether for big changes in Earth's history. And I think nothing is more shocking than cap carbonates. And those tell us about the snowball Earth glaciation. So a long time ago, the Earth got really cold. A lot of sort of aspects of our climate system ran away in the cold direction, and they sort of fed off of each other and accelerated the cooling of the Earth until most, if not all, of the Earth became encased in ice. And so one thing you can find in some parts of the world we call them tillites, till being the sediments that glaciers generate and deposit around. These just sort of big, chunky, heavy layers with large rocks in them. And so there's tillites, and then these tillites, they kind of accumulated, and then they have these big carbonate towers, these big layers of limestone that go on top of them, which start here and which are shown here. And so, Gavin, what caused those carbonates to form so suddenly?
Well, Graham, to put it a little bit more generally, the cool thing about these rocks that we're talking about today, these biogenic rocks, is that really they will form pretty much any time you get these big pulses of nutrients into the ocean. So in the case of the modern day algal blooms, they happen where you get a bunch of river water into the ocean, or where you get a bunch of upwelling of deep ocean waters that are more nutrient rich than the shallow ocean waters. But throughout Earth's history, sometimes you get more vast, distinct, stark pulses of nutrients into the ocean. And the cap carbonates formed when you, as you said, you covered the Earth in ice. And then as you melted it, basically you had none of these biological processes happening in the oceans before because they were covered in ice. And as you melted it, you just flush a bunch of stuff off the continents, a bunch of elements, a bunch of rocks into the oceans. And these critters are just so happy. They're just like waking up from hibernation, and they are just making shells, and they're making shells, and they're making shells, and they're making shells so quickly because there's so much nutrients and such a vast pulse that you get these giant carbonate layers in the rock record. So these very keen geologists of the 80s and 70s kind of walked around and were like, hey, why are these big stark carbonates in the rock record? And they figured out based on sort of the context that it was happening because you had snowball Earth. Like, you must have had something very different happening on Earth in order to get these big cap carbonates. And it turns out the Earth was covered in ice.
That's incredible. Oh my goodness. And to think that like these limestones are just telling us, they really can tell us so much about the Earth's history. And of course, we can't talk about biogenic rocks unless we talk about one of the most famous forms of biogenic components of rocks. Oh no, I did the wrong transition. We'll go to the next one, then we'll go back to Porcelanite because that's a close one to home. But fossils. Fossils are biogenic. They are parts of organisms that get caught up in the fossil record. So many folks will probably recognize this. This is a chunk of our Porcelain sandstone that's full of all these shells and sometimes bones. Another popular rock, local fossil hunting rock, is a Santa Margarita sandstone, which has great like oyster shells and all sorts of other great critters in there. And even sometimes we have much more, I think, exciting for most people, bones and bodies of vertebrate creatures, things like dinosaurs that we love that many folks are really quite excited about in Earth history.
Yeah, Graham. In a way, there's a lot more biogenic rocks than we had talked about today. We kind of focused on the rocks that are pretty much made up of these critters, right? Mm-hmm. But most sedimentary rocks, or I shouldn't say most, but many sedimentary rocks have fossils in them, because that's just kind of where fossils are sort of preserved. So many sedimentary rocks are biogenic in a way because they have these macro fossils. We call them macro because they're larger organisms, whereas the things that we were talking about today, the limestones of the world and the cherts of the world, those are micro fossils. They're still fossils though. They're just tiny.
I love it. I love it. And now we can talk about what I think is the coolest local sedimentary rock, porcelanite. And so, Gavin, what is porcelanite? It sounds kind of like porcelain. We know it looks kind of like porcelain, right? It's one of the key features of the Swift Street outcrop. It's this light colored, a little bit of like a grain to it, but otherwise really hard and rugged and smooth. What is this thing?
Well, Graham, I feel like it's aptly named because it really does look like porcelain. Mm-hmm. And the reason it looks like porcelain is because it's very high in silica. So in the layers of the local rock that you have porcelanite, we know that we have these silica-loving sort of critters that were in the water column when those rocks were being deposited. They were being deposited as sediments, but when those sediments were being deposited, they were silica-loving creatures. Think the diatoms of the world. And it's really cool because in this picture you can see that we had some transitions, right? It wasn't always that you just had those silica-loving critters in the ocean, right?
Right. And so we're sort of going between these kind of calcareous, clayey muds and porcelanite. And so here these sort of light-colored lumpy layers, or these really beige kind of lumpy layers, those are the mudstones. Those are sort of laying out. And then you have these really kind of blocky, really, really hard and rugged porcelanite layers that are in between those. And you can tell just how solid and silica rich they are because of how durable they are. But how come they don't look like that smooth chert, right? Sometimes you find these pebbles of this like dark reflective chert with these little like milky veins running through it. But the porcelainite, it's not that same smooth color. So what's different about that?
Well, Graham, it just is a function of the stuff you put into it, right? Well, obviously, but like in this case, or in church case, you're putting in mostly shells. Those are what geologists call siliceous oozes. Most of those muds that are forming that chert are silica. So it's just the amount of silica versus everything else. So in these porcelainite layers, you have relatively high amounts of silica when you compare them to the mudstones. But there's a lot of like clay and sort of dirt that is coming off the Santa Cruz coast, or the Paleo Santa Cruz coast, and sort of getting these porcelainite layers a little bit dirtier than what would make chert. I do want to add though, and Graham, I know that we've looked at this together. If you look really hard at the rocks in Santa Cruz, specifically the Swift Street outcrop that Graham and I love to talk about so much, there are tiny little chert layers. So these sort of coastal sections, these big, thick outcrops of coastal rocks are really good places to look at how the ocean has changed over time and how those ocean changes have caused critters to sort of behave differently in terms of whether they make their shells there or they don't.
Yeah, and I really appreciate that point, Gavin, because these biogenic rocks, these biogenic sedimentary rocks, are great ways to track environmental change through time, to see how conditions have allowed certain organisms to survive well and others not so well, and vice versa. So they're really important ways to sort of reconstruct the ecosystems of Earth's history.
Right, and because that's the case, a lot of paleoceanographers, or people who study how the oceans change through time, use these critters specifically to study just that, how the oceans have changed through time.
Well, I think they're such great rocks. And I think we've done them justice. And so we'll leave folks with our plug for next month's Rockin' Pop-Up. And this one is going to be explosive. It's going to go with a bang, because we're going to be talking about the formation of the moon.
Graham, well, we've been so close to home with all of the Santa Cruz rocks lately, the ocean-derived rocks. Let's go into space a little bit. The moon is a rock too, and I think that it'll be really fun to sort of see how it has formed over time.
I think that sounds great. We'll take a geology vacation out to the moon.
Well, I think you guys are out of this world, so that checks out for us here at the museum. I learned a lot at this one, and particularly that last little section about porcelainite I found really interesting, because I put a link in the comments about our new guide to the fossils of Santa Cruz County. So everyone watching, you can go look at that. And a big part of that guide is looking at these sedimentary formations that we have in Santa Cruz. And so I've been looking into the difference between the Monterey Formation, the Santa Margarita Sandstone, Santa Cruz Mudstone, Purisima Formation, and what you were just mentioning about the siliceous nature of aspects of the Santa Cruz Mudstone is interesting to me, because that's the same sort of thing that we see with the Monterey Formation, which is why people drill for oil into the Monterey Formation all up and down the coast, but we have it here too, up in the mountains and still like out at sea, I guess. And the Monterey Formation and Santa Cruz Mudstone seem quite similar to me as like in comparison to the Santa Margarita Sandstone, for instance. And they both kind of like formed farther off at sea, right?
Mm-hmm.
So they're millions of years apart, but kind of like similar conditions.
That's right. Yeah, and I think you hit the nail on the head when you said they form a little bit farther out to sea. So really what we're seeing is that the Santa Cruz Mudstone is pretty much purely a far out to sea type of rock. And did I say mudstone? The Santa Cruz Mudstone is an intermediate. The Monterey Formation, let me correct myself. The Monterey Formation is a far out to sea rock. the Santa Cruz mudstone is an intermediate. So you get sort of like this waxing and waning of the depth of the water column during that time. And the sandstone is really more coastal. So you're seeing just that, like a change in the water column through time over where those are formed.
Cool. And another local rock that you brought up, I guess we got a lot of biogenic geology that occurs around here in Santa Cruz, huh? Pretty cool. But another one you brought up earlier on was limestone and marble. And I just have a burning question for you too about our marble here in Santa Cruz, because I've heard that it's kind of like not really marble, but also kind of like not really limestone. Do you have anything to say about that? Is it like on its way to becoming marble, or?
I would say it's, and I could be mistaken here. This is just my own interpretation. But I would say it's marble. It's definitely not limestone, because if you look at a chunk of it, you've got these big calcite crystals in it. So it is like, it has recrystallized in a serious way. If we were to go knock off a true chunk of limestone, you could, polish it and look at it with a microscope, and you'd see little critters in there. You won't see any of those little critters here. What makes our marble not like, right, this isn't sculpting marble because it's dirty. This is an impure limestone in the way that like the Santa Cruz mudstone is kind of an impure mudstone. It's got some calcareous bits in it. So if you look at our Santa Cruz marble, there's lots of detritus in there. There's lots of stuff in there that isn't calcite, that isn't, calcium carbonate. And so that's what makes it not like, no one's gonna carve a beautiful sculpture out of it or build buildings out of it, because it's got these really blocky crystals. And then there's all sorts of just like geologic junk in there.
Yeah. I love the idea that these like kind of, maybe like diatomaceous rocks or, something like limestone that has its origins in life, that if you look close enough, you can actually see like the little corpses of that life in there. These little microfossils. I love that. Something you don't really think about. Well, if anyone watching has any questions, get them in there while you still can. In the meantime, I'm going to share that in the comments, I also dropped a link for an upcoming event that we're doing with some colleagues of Gavin and Graham up at UC Santa Cruz, where they do their thing. So also part of the Department of Earth and Planetary Sciences is the seismology lab. And so we are going to have an anniversary event next Thursday, March 11th, with Heather and Christina from the seismology lab. And they're going to be talking about the basically that like big tsunami event that kind of happened in Santa Cruz 10 years ago. We're going to be looking back on the earthquake that caused that, and how that tsunami affected Santa Cruz, and kind of like thinking about that phenomenon, since it's been 10 years already since that happened. So you can register for that event in the comments. I'm also going to drop a link to, we never do this, but I really hope that you all watching will take a moment to bear with me on this one. But I've got a survey link that I'm putting in there. Since we don't ask people to register for this event, we don't really like get a lot of, feedback, but I would really love to hear what you all think. And so if you could just take a minute or two to fill out this survey, would mean a lot to us. So that's in the comments. Lots going on there. Yes, this program is being recorded, and the one next week will be recorded too. We record all of our online offerings, and you can find them all on our website, including just dozens and dozens of Rockin' pop-ups that we've done. And someone says fascinating presentation. So
Thank you.
Good job. All right, I guess we will call it a day then. Thanks, gents.
Thank you.
All right, we'll see you next month. Happy March.